Some ancient technologies remain impossible for us to recreate. This video explores 20 advanced feats of engineering and craftsmanship from our distant past that modern science still cannot fully explain. By the end, you will gain a new perspective on human history, one where lost chapters reveal a depth of knowledge we are only beginning to appreciate. How did a 2,000-year-old device predict planetary movements with clockwork precision? And what secret ingredient made a Roman dome last longer than any modern structure? These are not just curiosities, but signposts pointing to forgotten peaks of innovation. What does it say about our own civilization when the past holds secrets we have yet to unlock? The story begins not in a laboratory, but in the clear blue waters off a Greek island. In the year 1900, sponge divers working near Antikythera stumbled upon a shipwreck from the ancient world, a vessel laden with statues and treasures. Among the corroded bronze and marble recovered was a lump of green, encrusted material that seemed unremarkable at first. It would take decades for researchers to realize they had found the single most technologically complex object from antiquity, a device that would shatter our understanding of ancient science. This is the Antikythera Mechanism. At its heart lies a system of at least 30 precise bronze gears, housed in a wooden case no larger than a shoebox. When a hand crank was turned, these interlocking gears moved dials and pointers across several faces, displaying a moving model of the cosmos as the Greeks understood it. It could predict the positions of the sun and moon, track the phases of our lunar neighbor, and even forecast eclipses with astonishing accuracy. It was, in essence, a mechanical computer built over 2,000 years before the modern computer age. The sophistication is in the details. Each gear tooth was cut by hand, and the ratios between the gears encoded complex astronomical cycles. One gear, for instance, modeled the moon's subtle wobble in its orbit, a motion called precession, which takes 18 years to complete. To achieve this with metal gears without the aid of electric tools or computer modeling represents a staggering leap of craftsmanship and theoretical knowledge. The metallurgy itself is a lost art, the bronze alloy precisely formulated to be both durable and workable for such miniature components. Historians and engineers who have studied reconstructions are unanimous. This was not a toy or a speculative model. It was a precision instrument. It likely served as a navigational aid for sailors, a calendar for religious festivals, and a demonstration of philosophical understanding for scholars. For perspective, technology of comparable mechanical complexity would not be seen again in Europe until the development of sophisticated clockwork in the 14th century, over a millennium and a half later. So how did this emerge in the 2nd century before the Common Era? The mechanism stands as a solitary masterpiece, with no direct predecessors or successors found in the archaeological record. It suggests a hidden lineage of Greek engineering, a school of thought focused on modeling the heavens through machinery, whose other works are lost to time. Was it a unique prototype, or a single surviving example of a more widespread technological tradition? The Antikythera Mechanism forces us to ask a profound question. If they could build this, what else did they know that we have simply forgotten? This question of lost scale and ambition leads us directly to our next mystery, a creation not of intricate gears, but of unimaginable weight and enduring grace. That same question of lost knowledge echoes within the silent, sunlit space of a building in Rome. The Pantheon's dome is a marvel of geometry, but its true miracle is the material from which it was cast. For nearly 2,000 years, this unreinforced concrete dome has withstood earthquakes, pollution, and the relentless passage of time without a single major repair. Modern concrete, by stark contrast, is engineered with steel rebar for strength, yet we see it crack, spall, and deteriorate within mere decades, especially in harsh marine environments. The secret to this ancient superiority lies not in what the Romans had, but in what they understood. Their concrete was a living recipe. While we use Portland cement, a processed material that reacts with water and then is essentially inert, the Romans mixed their cement with a special ingredient, volcanic ash from the region of Pozzuoli. This ash, called pozzolana, contains reactive minerals that create a remarkable chemical process. When mixed with lime and seawater, it forms a crystalline structure known as calcium aluminum silicate hydrate. This is not just scientific jargon, it is the key to immortality. This structure grows stronger over centuries as it continues to react with moisture in the air, actually healing tiny cracks that form. Modern materials scientists describe it with a sense of awe, noting that our own concrete does the opposite. It weakens as water infiltrates and rusts the internal steel. The Romans, whether by brilliant accident or profound empirical study, engineered a material that improved with age. They even used this knowledge practically, building harbors by pouring this concrete directly into the sea, where it would set and harden underwater into indestructible piers, some of which are still in use today. Modern laboratories have spent years trying to reverse engineer the exact formula and mixing process. While we have replicated some aspects, creating what we now call geopolymer concrete, we have not matched the Pantheon's specific, enduring blend. Our versions lack the same longevity, the same elegant resistance to the elements. The Pantheon stands not as a relic, but as a permanent challenge. It asks us why a civilization with satellites and supercomputers cannot rebuild what a 2,000-year-old society achieved with volcanic dust, lime, and seawater. This mystery of material science extends far beyond Rome, however, to a place where artisans worked with a substance so delicate, its very existence defies the logic of preservation. While Roman concrete defied time through chemistry, another ancient craft achieved a legendary sharpness that cut through history itself. Stories from the Crusades speak of Damascus steel blades with almost mythical properties, swords so finely honed they could cleave a knight's armor in two, and yet remain flexible enough to bend without breaking. The most famous test involved a single-edged saber and a silk scarf dropped onto its blade, the delicate fabric parting cleanly under its own weight. This was not fantasy, but the pinnacle of a metallurgical tradition born centuries earlier. The secret began not in Syria, but in India, with mysterious ingots of steel known as woots. These small, crucible-forged cakes of iron and carbon were traded along ancient routes, their mottled surface hinting at the potential within. In the forges of Persian and Arab swordsmiths, these ingots were heated, folded, and hammered with a rhythmic, patient artistry. The process was not just about shaping, but about coaxing a specific crystalline structure from the metal. Through cycles of heating and careful cooling, the carbon within the steel formed into microscopic patterns, resulting in the distinctive watery or ladder-like designs etched onto the finished blade, patterns that were as much a signature of strength as they were of beauty. Modern metallurgists examining these blades under electron microscopes have been stunned by what they found. The steel contains carbon nanotubes, incredibly strong structures at a molecular level that we associate with 21st century nanotechnology. Furthermore, trace impurities like vanadium, likely present in the original Indian ore, seem to have played a crucial role in forming these ultra-strong microstructures. The smiths of the medieval Islamic world had no concept of nanotechnology, of course. Their mastery was one of meticulous observation and tradition, passed down through generations. They learned to read the color of the metal in the fire, to listen to the ring of the hammer, achieving through skill and ritual what we now understand as advanced materials science. The knowledge was not lost in a single moment, but faded with the decline of the specific trade routes that supplied the woots ingots and the social structures that supported the master-apprentice lineages. As the forges cooled, the exact recipe, the precise temperature cycles, and the smith's intuitive touch vanished. Today, we can analyze the blades and even create modern alloys that mimic their appearance and some properties, but no one has fully recreated the exact combination of flexibility, resilience, and legendary edge retention of a true Damascus sword. It remains a masterpiece of lost art, where the hand of the craftsman guided processes we are still struggling to define with our most advanced instruments. This pursuit of impossible precision did not end at the forge, however. It found another expression in a place where stone was cut not with fiery force, but with a patience that seems to defy human scale. The legendary sharpness of Damascus steel met its match not in another blade, but in a wall. High in the Andes, the fortress of Sacsayhuaman presents a sight that stops modern engineers in their tracks. Here, stones weighing more than 100 tons are locked together in a sprawling, zigzagging rampart, each block a unique, irregular polygon. The true marvel is in the joinery. These colossal stones fit so perfectly that you cannot slip a single piece of paper between them, and this without a trace of mortar. For over 500 years, through relentless earthquakes that would shatter modern brick buildings, these walls have not budged an inch. The precision is so exact, so unforgiving, that it seems to defy the tools we know the Inca possessed, which were primarily stone hammers and bronze chisels. Archaeologists stand before these walls and ask the same simple, profound question: how the stones themselves, often quarried miles away across rugged mountain terrain, present the first mystery. How were these behemoths, some the size of small houses, transported and lifted into place without the wheel, without pulleys, without draft animals stronger than the llama? The theories are as varied as they are intriguing. Some researchers point to the possibility of advanced abrasives, perhaps using quartz sand and water to slowly grind the granite over years, a technique of sublime patience. Others speculate about a lost system of measurement and planning, perhaps using clay models or intricate chord records to map out each irregular block before a single chip was struck. More esoteric suggestions drawn from local oral histories even mention the concept of sonic levitation, where specific frequencies could soften stone or make it weightless. While this idea captures the imagination, it highlights the central dilemma. The practical method remains just out of reach. Look closer at sites like Ollantaytambo, where a row of 6 monoliths known as the Temple of the Sun sits on a high platform. Each pink granite slab is perfectly dressed and aligned, with subtle protrusions and indentations that interlock like a 3-dimensional puzzle. At Machu Picchu, the stonework graduates from massive foundational blocks to the refined ashlar masonry of the royal residences, showing a mastery that scaled from the monumental to the intimate. This was not brute force, it was a high art of stone, a language of geometry and pressure where every angle was calculated to distribute weight and resist seismic shock. The joints are so tight because the Inca understood that a rigid, mortared wall would crack under the Earth's movement, while their flexible, interlocking design would simply settle and readjust, a dance with the mountain that has lasted for centuries. This seamless joinery, this conversation with stone, forces us to look even further back. If the Inca achieved this 500 years ago, what does it say about stonework that is thousands of years older, where the blocks are not just precisely cut, but are of a scale that dwarfs human ambition? The silence inside the king's chamber is profound, a solid geometry of shadow and stone. Here, high within the heart of the Great Pyramid, you are surrounded by immense blocks of red granite, each one weighing more than 50 tons. The sheer physicality of the space is overwhelming, but the true mystery is not just the weight, it is the placement. How were these colossal slabs, along with the intricate network of passageways and the soaring incline of the Grand Gallery, assembled with such breathtaking accuracy over 4,500 years ago? Modern engineers who survey the structure report measurements that border on the impossible. the pyramid's base is aligned to true north with an error of just a fraction of a degree, a feat requiring astronomical knowledge we struggle to attribute to that era. The ratio of its perimeter to its height mirrors the mathematical constant pi, and its dimensions seem to encode the circumference of our planet. This is not random construction, it is architecture as precise equation. The greatest engineering puzzle, however, lies directly above your head in that silent chamber. To distribute the unimaginable weight of the masonry overhead and prevent the ceiling from collapsing, the builders constructed a series of 5 relieving chambers. These are stacked like attics above the king's chamber, each capped with gigantic granite beams. The challenge is almost incomprehensible. These beams, also weighing tens of tons each, had to be hauled up the already constructed interior to a height equivalent to a modern 20-story building, then perfectly maneuvered into a confined space. With only wood, rope, copper tools, and human muscle, how was this achieved? The dominant theory for the pyramid's main construction involves massive ramps, either straight on one face or wrapping around the structure. Yet, when applied to the interior's tight quarters and precise placements, the ramp theory begins to strain. The space within the Grand Gallery is too narrow for large work crews, and the angles are too steep for dragging such burdensome loads. This has led to more speculative ideas, from the use of internal spiral ramps that were later filled in, to sophisticated counterweight systems that acted like ancient elevators within the pyramid's core. Some researchers even point to evidence of water channels, suggesting a hydraulic lift method using the Nile's power. Each theory has its flaws, and none fully explain the seamless execution. Perhaps the most compelling clues are not in the grand design, but in the small artifacts left behind. In the ruins of a temple near the pyramid, archaeologists found a curious object, a small stone vessel with a delicate, flared rim. The craftsmanship is so fine, the walls so evenly thin, that it resembles work from a modern precision lathe. Yet it is carved from diorite, one of the hardest stones on Earth, harder than iron. The tools required to hollow out and polish such a vessel with the symmetry we see simply do not appear in the traditional archaeological record for that period. This artifact and others like it whisper of a forgotten practical science. They suggest the ancient builders may have possessed advanced abrasive compounds or vibration-based cutting techniques that have left no other trace. It forces a humbling question. Did they solve problems of mass and precision with methods so elegant, so unlike our own industrial approach, that we are still searching for their footprints in the dust? This search for a lost technical lexicon takes us from the dry heat of the desert to a very different environment, where another civilization performed miracles of stonework not with abrasives, but with a liquid fire that flowed like water. That question of a forgotten technical lexicon finds a strange echo not in stone, but in a simple clay jar. In the 1930s, workers excavating near Baghdad uncovered a small, unassuming artifact from the Pantheon era, around 2,000 years old. It consisted of a terracotta pot, a copper cylinder soldered with a lead-tin alloy, and an iron rod suspended inside the cylinder by an asphalt plug. To the untrained eye, it looked like a curious storage vessel, but to Wilhelm Koenig, the German archaeologist who first studied it, the arrangement was eerily familiar. He proposed a startling idea. What if this was an ancient electric battery? The concept is simple in principle. If the jar was filled with an acidic electrolyte, like vinegar or grape juice, a chemical reaction would occur between the two different metals. The iron rod would corrode, releasing electrons that would flow through the electrolyte to the copper cylinder, creating a small electrical potential between the two. Connect them with a wire and a tiny current would flow. Experimental archaeologists have tested this hypothesis by building exact replicas. When filled with a plausible ancient electrolyte, these replicas consistently produce a low voltage, around 1 to 2 volts. It is not enough to power a light bulb, but it is a measurable, usable current. So what possible use could such a faint trickle of electricity have served in antiquity? The most compelling theory points not to illumination but to gilding, the process of electroplating, where a thin layer of a precious metal like gold is deposited onto a baser metal like silver using an electric current, requires only a low voltage. There is intriguing, though not conclusive, evidence from the region. Some artifacts from the same period show gold plating on silver objects that is remarkably even and thin, a result difficult to achieve with traditional mercury-based fire gilding, which leaves a thicker, less uniform coating. Could these jars have been connected in series to produce a stronger current, allowing a craftsman to silently plate intricate jewelry with a flawless golden finish? Skeptics, of course, offer a more mundane explanation. They argue the device was simply a secure storage container for sacred scrolls, with the iron rod acting as a core around which parchment could be rolled. The asphalt seal, they note, would have kept out moisture. This is a perfectly reasonable interpretation, and the truth is we may never know the jar's original purpose with absolute certainty. Yet the existence of similar finds, including jars with more complex internal arrangements, suggests these were not one-off curiosities. The very possibility forces a profound reconsideration. If the Parthians, or a culture before them, were experimenting with basic electrochemical principles, it hints at a branch of practical science that existed completely outside our traditional historical narrative. It was not about powering cities, but perhaps about perfecting art, about achieving a subtle, beautiful effect through the invisible movement of particles. This quiet, potential mastery of an unseen force makes the next mystery all the more striking, for it deals with a technology that did not create energy, but captured and bent it, transforming the very nature of light itself. The invisible currents of a Baghdad jar hint at a quiet mastery of chemistry, a theme that emerges again in a story that seems plucked from myth. The Roman historian Petronius recounts a curious tale in his Satyricon. A humble glassmaker secured an audience with Emperor Tiberius, presenting him with a singular creation, a drinking bowl crafted entirely from glass. The emperor, intrigued, examined it before deliberately dashing it to the marble floor. Instead of shattering into 1,000 pieces, the vessel merely dented. With a few light taps from a small hammer, the glassmaker promptly restored it to its original shape. This was vitrum flexile, flexible glass. Tiberius, after the demonstration, asked a pointed question whether any other living soul knew this formula. Assured it was a secret held by the craftsman alone, the emperor, fearing such a material would devalue gold and silver, ordered the man executed, and with that the secret was lost forever. This story is often dismissed as mere fable, an ancient tall tale. Yet materials scientists today pause at its details. Could it have been possible? Glass as we know it is an amorphous solid, a frozen liquid. Its rigidity and brittleness come from its chaotic molecular structure. To make it flexible, you would need to introduce something to impart plasticity, to allow the atomic bonds to stretch and reform without breaking. Modern researchers speculate about potential avenues the Roman artisan might have explored. One theory points to the addition of specific metallic oxides, like manganese or even beryllium, during the molten stage. In precise quantities, these additives could potentially alter the crystalline behavior of the silica, creating a glass-ceramic hybrid with some ductile properties. Another possibility is a form of ultra-thin glass, which can indeed bend significantly before fracturing, though the story describes a sturdy drinking vessel, not a delicate film. The historical record offers a faint, tantalizing clue. Roman glasswork from that era sometimes exhibits exceptional durability and clarity, achievements credited to their mastery of manganese dioxide as a decolorizing agent. This practical knowledge of chemistry was profound, Could an experiment with proportions have accidentally yielded a batch with unexpected flexibility? The truth is, we have no archaeological evidence of vitrum flexile, no bent glass bowl in a museum case. This leads many experts to conclude it was likely an allegory about the dangers of innovation in an autocratic state, or a misunderstanding of another material like clear, hardened leather or early polymer like resins. But the story persists because it speaks to a deeper truth about the Roman world, their relentless experimentation with materials. They were not just builders and soldiers, they were practical chemists, constantly testing the limits of natural substances. Whether the flexible glass was real or legend, it reflects a culture that believed such a material was within the realm of possibility. That same spirit of material innovation appears elsewhere in the ancient world, in objects that seem to defy the very passage of time through their impossible preservation. The legend of a glass that could bend without breaking speaks to the ancient world's hidden experiments with matter, but one formula was guarded with such deadly secrecy that its exact composition remains a mystery to this day. For the sailors of the Byzantine Empire, fire was not just a weapon, it was a living nightmare unleashed upon the sea. Imagine the terror of a medieval naval crew watching an enemy Droman warship approach, not to ram, but to spray a jet of liquid flame across the water. This was no ordinary fire. It clung to the wooden hulls and sails. It burned with a fierce, roaring intensity even on the waves themselves, and according to desperate accounts, water seemed only to spread it further. This was Greek fire, the Byzantine Empire's most closely held state secret and the key to its naval dominance for over 7 centuries. Historical records, particularly from the siege of Constantinople in the 7th century, describe its deployment through bronze tubes mounted on the prows of ships, siphons that could project the fiery stream with a terrifying hiss and roar. Some accounts even mention handheld versions like early flamethrowers used to repel boarders. The psychological impact was as devastating as the physical damage. To face it was to face an element that defied the natural order, a fire that water could not quench. So what was in this apocalyptic concoction? Modern chemists and historians have pieced together likely components from scattered references and the known trade of the era. The base was almost certainly a form of crude petroleum or naphtha, a light, flammable liquid that could float on water. This would explain its clinging, persistent burn. To this, the Byzantine chemists likely added other ingredients to create its infamous properties. Quicklime, for instance, reacts violently with water, generating intense heat and potentially igniting the petroleum on contact with seawater. Other suggestions include resin or pitch to make it sticky, and perhaps even saltpeter to introduce an early form of oxidization, making it harder to smother. The exact recipe and the precise mechanism of the pressurized siphon, however, were secrets of such immense strategic value that they were known only to a select few, possibly even a single family. Emperors went to extraordinary lengths to protect the knowledge, compartmentalizing the manufacturing process so that no single artisan knew the complete formula. This obsessive secrecy worked too well. When Constantinople finally fell in the 15th century, the last custodians of the art of Greek fire seemed to have vanished, taking the definitive instructions with them. We can approximate its effects with modern chemicals, but we cannot replicate the exact, battlefield-tested blend that gave the Byzantine navy its invincible shield. It stands as a stark reminder that some technologies are lost not to the erosion of time, but to the deliberate and successful silence of those who understood their power. This mastery of controlling a powerful and terrifying force finds a strange parallel in another ancient innovation, one that sought not to unleash chaos, but to shape something equally fundamental, the very nature of sound itself. The terrifying hiss of Greek fire was a weapon of pure chaos, but in the jungles of the Americas, another civilization mastered a very different kind of wave. At the ancient Mayan city of Chichen Itza, If you stand at the base of the Great Pyramid known as El Castillo and clap your hands, something extraordinary happens. The echo that returns is not a simple reverberation of your own sound. It is a sharp, chirping descent that uncannily mimics the cry of the sacred Quetzal bird. This is not an accident of architecture. It is acoustic engineering carved in stone, a deliberate fusion of sacred geometry and wave physics that we are only beginning to decode. Archaeologists and acoustic physicists who have studied the site confirm the phenomenon is a direct result of the pyramid's precise step design. Each of the 4 staircases consists of 91 steps, and when sound waves from a handclap hit these staggered, evenly spaced surfaces, they scatter and reflect in a specific sequence. The time delay between the reflections, combined with the angle of the stairs, creates a series of rapidly descending frequency echoes that our ears perceive as that distinctive chirping sound. The builders of El Castillo sculpted the very air itself, embedding a symbolic animal call into the heart of their most important ceremonial structure. The implications are profound. The Quetzal bird, with its resplendent green feathers, was deeply associated with the serpent deity Kukulkan and with the concept of divinity itself. During equinox ceremonies, when the shadow of the serpent appears to slither down the pyramid staircase, the ritual would have been a multisensory experience. The visual spectacle of light and shadow would have been accompanied by this auditory manifestation, the call of the divine bird emerging from the stone as if by magic, reinforcing the sacred connection between the heavens, the earth, and the ruler who stood at the apex. This sonic precision was likely not limited to Chichen Itza. Reports from other Mayan sites, like the pyramid at Tikal, suggest similar intentional acoustic effects, where certain spots amplify whispers or create resonant frequencies that could alter a participant's state of awareness during rituals. Some researchers theorize that these acoustic properties might have even been used in concert with astronomical observations. A chant or a drumbeat from a specific platform at a specific time could have produced standing waves or echoes that marked celestial events, turning the entire city into a kind of stone calendar you could hear. This represents a sophisticated, applied understanding of sound wave behavior that predates modern acoustical science by over 1,000 years. They were not just building monuments to be seen, but to be heard and felt, encoding knowledge not in text alone, but in the physical interaction between their architecture and the environment. This concept of embedding function into form reaches its most enigmatic expression in another part of the world, where the goal was not to create sound, but to achieve a silence and a balance so perfect it seems to defy gravity itself. A book exists that has stared back at scholars for 600 years, refusing to give up its secrets. The Voynich Manuscript is a small, dense codex of over 200 pages, filled from edge to edge with flowing, elegant script in a language no one on earth can read. Its pages are a garden of the impossible, illustrated with plants that have no known counterpart in nature, roots and leaves twisting in alien configurations alongside astrological charts and intricate diagrams of what appear to be biological or celestial systems. Carbon dated to the early 15th century in northern Italy, its very existence is a sustained provocation to our understanding of history. Who wrote it and for what unimaginable purpose? The text itself is the core of the mystery. It consists of a unique alphabet of roughly 30 characters, written with a natural, fluid hand that suggests the author was not inventing symbols on the spot, but was deeply familiar with the script. Statistical analysis by modern linguists and computer scientists reveals a startling pattern. The words follow what is known as Zipf's law, a linguistic principle where the most common words in a natural language appear with predictable frequency. The Voynich text exhibits this property perfectly, suggesting it is not random gibberish, but a structured communication system with the internal logic of a real language. This finding has made it the ultimate cryptographic puzzle, attracting the attention of professional codebreakers from both world wars and, more recently, the most powerful artificial intelligence algorithms. Yet every attempt has ended in failure. Artificial intelligence systems trained on hundreds of languages can detect the manuscript's structural patterns, but cannot map its symbols to any known tongue or cipher key. It is as if the book is speaking in a coherent voice, but we are utterly deaf to its meaning. The theories attempting to explain it are as varied as its strange illustrations. Some propose it is an elaborate, centuries-old hoax, crafted to defraud a wealthy patron. Yet the statistical evidence of linguistic structure makes a meaningless hoax incredibly difficult to sustain over 200 pages. Others suggest it is a lost language, perhaps a constructed one, or a system of shorthand for recording herbal or alchemical knowledge, meant only for a select few initiates. There is even a compelling theory that the text is a form of steganography, where the apparent words are a mask and the true information is encoded in the subtle details of the illustrations themselves. Each hypothesis raises more questions than it answers. If it is a hoax, why invest such staggering effort into a work of such intricate, beautiful nonsense? If it is a real treatise on botany, why depict plants that never existed? The Voynich Manuscript is more than a puzzle, it is a mirror. It reflects our own deep need to understand and our profound frustration when the past presents us with a locked door for which we cannot find the key. It represents a complete system of information storage that we can see but cannot access, a library of knowledge whose catalogue has been erased. This frustration with an unreadable record leads us to a different kind of mystery, one not of information, but of an object whose physical dimensions seem to contain a message we are only beginning to hear. The Voynich Manuscript is a locked library of unreadable knowledge, but at a wind-swept plateau in Bolivia, the stones themselves seem to speak a language of impossible geometry. Pumapunku, part of the greater Tiwanaku complex, is not a grand pyramid or a soaring temple, but a field of shattered, bewildering precision. Scattered across the high-altitude plain are massive blocks of andesite and red granite, some weighing over 100 tons, but it is their condition, not their size, that stops the heart. These stones are not merely broken, they are dissected with a clinical, almost surgical accuracy that defies the era of their creation, over 1,000 years ago. The most iconic are the so-called H-blocks, immense stone modules with a series of perfectly identical, recessed niches. When you examine the edges of these cuts, you find something that should not exist. The grooves are ruler straight, the corners are sharp 90-degree angles, and the surfaces are flawlessly flat and smooth, with a uniformity that suggests the work of a modern milling machine or a diamond-tipped saw. There is no chisel chatter, no uneven scoring from hand tools. The finish is polished to a degree that feels industrial. Even more perplexing are the intricate channels and notches carved into these blocks, some only a few millimeters wide, which appear to be part of a complex interlocking system. Expert stonemasons and engineers who visit the site often express a shared, profound confusion. They point to drill holes that are perfectly cylindrical, with no deviation, and to T-shaped slots that are cut with such precision that separate stone pieces could theoretically slot together without mortar, forming a seamless, earthquake-resistant whole. The fundamental question is one of tools. The Tiwanaku culture, which flourished here, had access to bronze, a metal too soft to cut granite or andesite, some of the hardest stones on Earth. Copper chisels would be blunted in minutes against such material. So what did they use? The leading theories all point toward a mastery of abrasives far beyond simple sand. Some researchers speculate about the use of diamond-tipped tools, as diamonds are one of the few natural materials that can cut granite. While diamond deposits exist in the region, shaping diamonds into effective cutting edges presents its own immense technological hurdle. Others propose a lost formula for an ultra-hard abrasive paste, perhaps combining crushed quartz with a corrosive plant-based agent that could chemically assist in the grinding process. There is also the haunting possibility of a technique we have not yet conceived. Could they have used a method of thermal shock, heating the stone in a precise line and then cooling it rapidly to induce a clean fracture, or perhaps a form of sonic vibration, as some oral traditions suggest, to literally soften the stone for working? The evidence on the ground offers no easy answers, only silent, impeccable craftsmanship. One particular stone module, often photographed, displays a series of complex geometric cutouts that look like a template for a three-dimensional puzzle. The repeatability of the shapes, the absolute consistency from one niche to the next, speaks of standardized production, not one-off artistry. This suggests the builders of Pumapunku were not just skilled artisans, but engineers working from detailed plans, executing a design that required interchangeable parts. To achieve this with the technology we attribute to them is, by our current understanding, an anomaly. It stands as a stark, physical rebuke to our linear view of technological progress. The stones of Pumapunku do not whisper their secrets. They state them in a language of perfect angles and mirror-smooth surfaces, a language we have yet to fully translate. This mastery of moving and shaping incredible mass leads us to an even grander question, one found in the shadow of a single, uncut stone. The silent perfection of Pumapunku stones presents a puzzle of precision, but on a remote island in the vast Pacific, the challenge was one of sheer mass and distance. Easter Island's iconic Moai statues stand with their backs to the sea, their heavy-lidded gazes fixed inland, guardians of a culture that performed one of history's most staggering logistical feats. These are not just heads but full-bodied figures carved from volcanic tuff, with the largest completed statue weighing an estimated 82 tons and standing over 30 feet tall. The central mystery is not their creation but their journey. The quarry at Rono-Roroku is a mountainside workshop littered with nearly 400 statues in various stages of completion. From this single source, finished moai were transported across miles of rugged, rolling terrain to ceremonial platforms called ahu, some as far as 11 miles away. With no metal tools, no wheels, and no large animals to serve as beasts of burden, how did the Rapa Nui people accomplish this? For decades, the dominant theory involved a slow, arduous process of dragging the statues on wooden sleds or rollers across lubricated tracks made from the island's native trees. This method, while plausible, requires immense coordinated labor and a vast amount of timber, a resource that historical evidence suggests became desperately scarce on the island over time. Then a compelling alternative emerged, the walking theory. Proposed by archaeologists Terry Hunt and Carl Lipo, this idea suggests the moai were literally walked to their platforms. In experiments, teams using only 3 strong ropes and a rhythmic rocking motion were able to maneuver a concrete replica in an upright position, making it sway from side to side and pivot forward in small, incremental steps. This method would require far fewer people and less wood, aligning better with the ecological constraints the islanders eventually faced. Yet, even this elegant theory is not without its critics, who point to the risk of catastrophic damage to the fragile stone bases and the lack of clear archaeological evidence, like worn path grooves consistent with such a gate. The truth may lie in a combination of methods, adapted over centuries as resources changed. What is undeniable is the profound cultural drive behind this effort. The moai were not mere monuments, they were sacred repositories of ancestral spirit known as mana. Erecting one on an ahu was an act of communal power and devotion, linking the living community to the protective presence of their forebears. The investment of time, food, and human energy was astronomical, a societal commitment that speaks to the very core of Rapa Nui identity. This universal drive to move the immovable connects Easter Island to every other culture we have explored. From the multi-ton stones of Sacsayhuaman to the granite beams in the Great Pyramid, humanity has repeatedly dedicated its greatest collective efforts to transporting the seemingly unmovable, proving that the most advanced ancient technology was often not a tool, but the unwavering human will to honor something greater than oneself. That same will to shape the world according to a sacred blueprint finds expression in a different form, not in moving stone, but in aligning it perfectly with the cosmos above. Deep in the humid jungles of Costa Rica's Diquis Delta, workers clearing land for a banana plantation in the 1930s uncovered something utterly inexplicable. Scattered across the landscape, half buried in the earth, were dozens of massive stone spheres. They were not roughly shaped boulders, but objects of breathtaking geometric perfection, spheres carved from solid granite with a precision that seemed to defy their ancient origins. These are the stone spheres of Costa Rica, and they represent a manufacturing mystery that has puzzled archaeologists for nearly a century. The spheres vary dramatically in size, from as small as a baseball to colossal examples over 2 meters in diameter, weighing more than 16 tons. It is their form, however, that truly astonishes. Using modern laser scanning technology, researchers have measured many of the spheres and found them to be almost perfectly round, with surface variations of less than 2 millimeters. To achieve this level of sphericity without the aid of precision measuring tools, without metal, and without the wheel is an engineering accomplishment that borders on the surreal. How did the pre-Columbian peoples of this region, who left behind no written records, accomplish such a feat? The leading theory involves a process of immense patience and skill. Craftsmen likely selected large boulders of gabbro, a coarse-grained granite, and then used a technique of pecking and grinding. They would have hammered the stone with other, harder rocks to rough out a spherical shape, then painstakingly ground the surface smooth using sand and water as an abrasive, perhaps over the course of years. Some researchers suggest a more advanced method might have been employed, such as controlled thermal fracturing. By building fires against specific points on the stone and then rapidly cooling them with water, they could have caused thin layers to spall off, allowing for more controlled shaping before the final grinding phase. Yet even with these methods, the final step of achieving near-perfect roundness remains a profound puzzle. Did they develop a form of measurement using cords or wooden templates to constantly check their progress, a kind of Stone Age quality control? The purpose of these spheres is equally enigmatic. When first discovered, many were found arranged in geometric patterns, often in lines or triangles, or aligned with cardinal points. Tragically, most were moved from their original positions by later landowners, who used them as decorative lawn ornaments, destroying the archaeological context forever. This loss is irreparable, as those original arrangements likely held the key to their meaning. Some archaeologists propose an astronomical function, suggesting the alignments could have marked solstices or tracked celestial bodies, turning the landscapes into vast observatories. Others see a social or territorial significance, with the spheres acting as markers of power, lineage, or sacred spaces for the complex chiefdoms that flourished in the area. Their flawless, uniform shape might have symbolized cosmic perfection, communal unity, or the enduring power of a ruling family. They are a silent language carved in granite, a code we can no longer decipher because we lost the map. Their spherical perfection stands as a testament to a culture that valued ideal form, that invested generations of labor into creating objects of pure geometry, not for any obvious utilitarian purpose, but perhaps to make a permanent statement about order, balance, and their place in the universe. This drive to encode celestial knowledge into the very landscape, to build a permanent dialogue between earth and sky, finds its most ambitious and enduring expression in a desert where the lines drawn on the ground are so vast they can only be understood from the heavens. A disc of bronze etched against the dark earth holds a map to the heavens. In 1999, treasure hunters using metal detectors on a hill in Germany uncovered what looked like a piece of scrap metal, its surface caked with green patina. They had no idea they were holding a revolution in our understanding of the ancient European mind. The Nebra Sky Disc, dating to around 1600 years before the Common Era, is a stunning work of Bronze Age cosmology, a portable observatory cast in metal. It is considered the oldest known realistic depiction of the cosmos anywhere in the world. The disc itself is a dark bronze circle about the size of a large dinner plate, and upon its surface are applied symbols of pure gold. A central cluster of 7 stars is widely interpreted by astronomers as the Pleiades constellation, a crucial marker in ancient agricultural calendars across many cultures. A large golden circle represents the sun, or perhaps a full moon, and a crescent shape beside it depicts a lunar phase. But the most telling additions are 2 golden arcs along the edges, later added to the original design. These arcs, each spanning about 82 degrees, are believed to mark the solstices, the extreme points on the horizon where the sun would set between summer and winter. If you stood on that hill in Nebra with the disc aligned to the landscape, it would have told you precisely when to plant and when to harvest, turning celestial motion into a practical guide for survival. This was more than a calendar, however. It was a unifying symbol of knowledge and possibly power. The disc was found alongside 2 ornate swords, axes, and bracelets, suggesting it was part of a ceremonial hoard, perhaps belonging to a chieftain or a priest-king whose authority was linked to his ability to read the sky. The knowledge encoded in its gold placements is sophisticated, requiring generations of precise observation to note the subtle 18.6-year cycle of the moon's path and the seasonal position of the Pleiades. This artifact shatters the old image of prehistoric Europe as a realm of isolated, primitive tribes. Instead, it reveals a network of shared astronomical understanding, a common language of the stars that connected communities across vast distances. The Nebra Sky Disc is a testament to the human drive not just to observe light, but to capture its meaning in a permanent, physical form. This profound relationship with light, from marking its journey across the sky to attempting to manipulate its very substance, leads us to a final, shimmering mystery from a culture that sought to trap sunlight within stone itself. The drive to encode meaning into a permanent form finds one of its most beautiful and baffling expressions on a small island in the Mediterranean. In 1908, archaeologist Luigi Pernier was excavating the Minoan palace of Phaistos on Crete when his team uncovered a flat, fired clay disc about 6 inches in diameter. Its surface was covered on both sides with a spiraling sequence of symbols, a total of 241 impressions, arranged in groups that seemed to form distinct words. This was the Phaistos Disc, and it remains one of the greatest linguistic puzzles ever unearthed. What makes this object so extraordinary and so utterly frustrating to scholars is its complete isolation. Every single one of its 45 distinct symbols, depicting human figures, animals, plants, and abstract shapes, was not carved or painted, but stamped into the soft clay with individual seals before firing. This means the disc represents an astonishingly early form of movable type printing, a technology that would not become widespread for another 3,000 years. Yet, this revolutionary method appears nowhere else in the Minoan world. No other stamped document, no cache of the printing seals themselves has ever been found. It is as if this single object fell out of time, a lone prototype with no past and no future. Philologists who have studied the disc describe it with a sense of profound intrigue. The symbols themselves are unique, though a handful bear a vague resemblance to characters from other Aegean scripts, like linear or the hieroglyphs of ancient Crete. But the language they encode is a complete mystery. The text runs in a spiral from the outer edge toward the center, and the groupings are marked by short vertical lines, clearly separating what experts believe are individual words. The pattern suggests a structured message, not random decoration. So what does it say? The theories are as varied as the symbols themselves. Some researchers, noting the frequent appearance of a helmeted head, propose it is a military document, perhaps a roster of troops or a report from a campaign. Others, seeing the recurrence of a bee and a ship, suggest it could be a commercial inventory or a prayer for safe sea voyages. There is a compelling theory that it might be a religious hymn or a magical incantation, meant to be read aloud in a ritual context. A more playful idea posits it could be the rulebook for a forgotten board game, the spiral representing the path of play. The truth is, without a bilingual text, a Rosetta Stone for the Phaistos Disc, every translation attempt remains speculative. Modern computational analysis has been applied, searching for patterns that might reveal its linguistic roots, but the data set is simply too small. With only 241 signs, there is not enough material for statistical methods to find a definitive match to any known language family. This singular artifact stands as a silent sentinel. It proves that someone, in the Bronze Age palace of Phaistos, conceived of a system to reproduce written information quickly and uniformly, a conceptual leap toward the printing press. Yet that spark of innovation seems to have died the moment the clay hardened. Was the disc a secret diplomatic message from a foreign land, using a script unknown even to other Minoans? Was it the experimental work of a single ingenious scribe, whose technique was never adopted? We may never know. The Phaistos Disc is a complete system of communication that we can see but cannot hear, a captured thought from a world that remains just out of reach. This mystery of a controlled, internal environment crafted for a specific purpose leads us to a final ancient marvel, one that did not seek to preserve words, but to defy an entire climate. A cool breeze descends in the heart of a desert city, drawn down from a tower that seems to listen to the sky. This is the magic of the Badger, the Windcatcher, an architectural invention that turned the punishing heat of ancient Persia into a manageable, even comfortable environment. But the Windcatcher was just the visible part of a brilliant, integrated system, a masterpiece of passive engineering that provided natural air conditioning, refrigeration, and even ice production centuries before the invention of the electric compressor. This was not magic, but a profound understanding of physics woven into the very fabric of cities. The system worked in an elegant synergy. The Windcatcher, a tall chimney-like structure with vents oriented to catch prevailing winds, would capture the slightest breeze high above the ground. This air was then funneled down a central shaft, often passing over a pool of water or through a channel connected to a kanat. The kanat was a separate marvel, a gently sloping underground aqueduct that tapped into mountain aquifers and transported water for miles without a single pump, using only gravity. Where the cool, moist air from the kanat tunnel met the air being pulled down by the Windcatcher, a beautiful thermodynamic event occurred. The dry desert air would cause rapid evaporation from the water's surface, and evaporation always absorbs heat. This process chilled the air significantly, sometimes by 20 degrees or more, before it was released into the living spaces or storage rooms below. The result was a continuous flow of cool, fresh air, a sanctuary from the blistering sun outside. But the Persians did not stop at cooling air, they aimed to preserve cold itself. Enter the Yakchul, the ice pit. These were massive, dome-shaped structures, often built partially underground, with thick walls made from a special heat-resistant mortar called saruj, a mix of clay, sand, ash, and egg whites. During the cold winter nights, water from the kanats was channeled into shallow pools where it would freeze. This ice was then harvested, broken into blocks, and stored deep inside the Yakchul. The design was genius. The thick, insulating walls and the subterranean placement kept the interior temperature stable, while a trench at the base of the dome would drain any meltwater, which would then refreeze during the night, creating a self-sealing cycle. Some of these ice houses could preserve ice well into the scorching summer months, providing a luxury we take for granted today. This was a fully sustainable, zero-energy climate control system, a network of wind, water, and earth working in concert. It transformed cities like Yazd and Kashan into livable oases and allowed for the storage of perishable food and medicine. The architectural integration was seamless, with windcatchers rising gracefully from the roofs of homes, mosques, and bazaars, while the life-giving qanats ran silently beneath the streets. This ancient approach to thermal regulation stands as a quiet rebuke to our energy-intensive modern methods, a reminder that sometimes the most advanced technology is the one that works in harmony with nature, not against it. This same pursuit of harmony, of bending the elements to human will through deep understanding, finds a parallel in a much smaller, yet infinitely more intricate realm of creation. In the heart of Delhi, a 7-meter-tall sentinel of iron has stood guard for over 1,600 years, defying the very chemistry that destroys its modern counterparts. The iron pillar of Delhi shows not a single flake of rust, its surface bearing only a dark, protective patina that has kept it pristine through monsoons and pollution. This is not a miracle of chance, but a masterpiece of forgotten metallurgy. Forged in the 4th century, the pillar is composed of an exceptionally pure wrought iron, but its secret lies in a specific impurity. Ancient smiths, working without modern chemical analysis, crafted an alloy with an unusually high phosphorus content and a very low sulfur content. This precise combination is the key to its immortality. When exposed to the air, the phosphorus in the iron reacts to form a thin, stable layer of iron-hydrogen phosphate hydrate. This film, only a few microns thick, acts as a self-healing shield. If scratched, the local chemistry allows the protective layer to reform, preventing oxygen from reaching the raw metal and initiating the destructive process we know as rust. Modern corrosion scientists only began to understand this mechanism, known as passive film protection, in the 20th century. The pillar's preservation is also a testament to its environment and its construction. It was likely forged by a process of welding together small lumps of hot iron under immense hammers, a technique that created a dense, slag-free metal. Furthermore, the dry, relatively stable climate of Delhi for much of its history provided the ideal conditions for that initial protective film to establish itself and endure. Attempts to replicate this specific anti-corrosion property in modern steel have been only partially successful. While we can create phosphorus-rich alloys, achieving the same flawless, self-regenerating passive layer on an industrial scale and in harsher, wetter climates remains a significant challenge. The pillar thus stands not just as a monument to a Gupta king, but as a symbol of a deep empirical science. Its creators understood the behavior of their materials on a level we are still working to decode, achieving through artisanal intuition what our laboratories strive for with precise instrumentation. This mastery of material on a monumental scale finds its echo in an endeavor of even greater ambition, one that required moving not just purified metal, but mountains of earth. From the cool, engineered air of a Persian windcatcher to the silent endurance of an iron pillar, we see a pattern of ancient mastery over environment and material. This same desire to leave a permanent mark on the world, but on a scale that defies ground-level comprehension, brings us to the high desert of Peru. Here, the earth itself becomes a canvas for messages only visible from the heavens. The Nazca Lines are a sprawling gallery of geoglyphs, massive drawings etched into the rocky, arid plateau by removing the dark surface stones to reveal the lighter earth beneath. They depict a stunning array of forms, from geometric shapes like trapezoids and spirals that stretch for miles, to intricate representations of animals, plants, and even a humanoid figure often called the astronaut. The hummingbird, with its long, delicate beak and outstretched wings, is a masterpiece of flowing lines. The spider, with one leg elongated in a precise, purposeful direction, is rendered with an anatomical accuracy that suggests deep observation. These are not small carvings, they are monumental artworks on a landscape scale, some figures longer than 3 football fields placed end to end. The central, enduring mystery is how the Nazca people, who flourished between 200 years before and 600 years after the start of the Common Era, created such precise, colossal images without ever seeing them from above. They had no flight, no balloons, no way to view their work from the vantage point that makes it comprehensible to us. So how was it done? Archaeologists like Maria Reich, who dedicated her life to studying the lines, demonstrated that the technology was deceptively simple in its components. The creators likely used wooden stakes and ropes to plot out the designs. Starting from a central point or a carefully scaled model, they would have used basic surveying principles, perhaps aligning stakes with distant mountain peaks or using measured pacing to transfer the proportions of a small sketch to the gigantic desert floor. By clearing away the dark, oxidized stones along these plotted lines, they created the sharp contrast we see today. The true sophistication was not in the tools, but in the communal execution and the mathematical understanding of scale. Maintaining the perfect curvature of a monkey's tail or the symmetry of a condor's wings over a kilometer of rugged terrain required extraordinary planning and coordination. It was a project of generations, a cultural tradition of marking the earth according to a shared vision. But for what purpose? The theories are as vast as the drawings themselves. One prominent idea is astronomical, that the lines functioned as a giant calendar, aligning with the rising and setting of the sun, moon, and specific stars like the Pleiades to mark important agricultural or ceremonial dates. Another suggests they were ritual pathways, walked by participants during sacred ceremonies to connect with deities or ancestors, the very act of walking the lines being a form of prayer or pilgrimage. A more speculative theory posits they were messages intended for the gods themselves, who dwelled in the sky and could look down upon the offerings etched into the earth. The most compelling answer may encompass all of these, seeing the Nazca Plateau as a sacred landscape, a text written in lines and figures that integrated astronomy, religion, and community identity. The knowledge of how to create these geoglyphs, the precise measurements and alignments, would have been passed down through specialized groups within the culture, a sacred geometry preserved in oral tradition and ritual practice. Their survival for 2 millennia is a testament to the stable, arid climate, where rain is so rare that the cleared lines are never washed away. They stand as the ultimate expression of large-scale artistry, a collaboration between human intention and a canvas provided by the planet itself. This leads us to our final physical mystery, a creation that pushes the very concept of ancient engineering into a realm that feels almost otherworldly. A warrior stands on the deck of a longship, the storm-tossed sea a gray expanse behind him. In his hand, he does not hold a simple iron blade, but a weapon of legend, a sword marked with a name that carried the weight of destiny. Etched into the steel near the hilt is a single, powerful word, Ulfberht. This was not just a label, it was a guarantee. In an age where many swords were brittle, prone to bending or shattering in the chaos of a shield wall, the Ulfberht was something else entirely. It was a sliver of technological superiority that must have felt almost supernatural to those who faced it. These swords, produced between the 9th and 11th centuries, represent a metallurgical leap that isolated them from the rest of medieval Europe. The secret was in the material. Most European swords of the Viking era were forged from what is called bloomery steel. This process involved heating iron ore in a charcoal fire, producing a spongy mass of metal mixed with slag, the rocky impurities from the ore. The blacksmith would then try to fold and hammer out these imperfections, but the result was still an inconsistent, often brittle steel with a low and uneven carbon content. An Ulfberht blade was different. It was made from what we now term crucible steel. The raw iron was melted at an extremely high temperature, far beyond what typical European forges could achieve in a sealed clay crucible. This allowed the slag and impurities to fully separate and rise to the top, leaving behind a pool of pure, liquid steel with a remarkably high and uniform carbon content, around 1.5%. This is a carbon level comparable to modern high-quality steel. The result was a blade of extraordinary performance. It was both harder and more flexible than its contemporaries. It could take a sharper, more resilient edge that would hold in battle, and its flexibility meant it could absorb the shock of a heavy blow without snapping. In the hands of a skilled warrior, it was the difference between a trusted tool and a liability. The mystery deepens when we ask where this material came from. The Vikings did not possess the furnace technology to produce crucible steel themselves. Metallurgists who have studied the blades point the finger eastward, to the trade routes that connected the Viking world to Central Asia, specifically to the region of modern-day Iran and Afghanistan. There, a method for creating high-carbon crucible steel, known as woots, had been practiced for centuries. It is likely that Viking traders acquired ingots of this prized material along the river routes to the Caspian and Black Seas, transporting the raw potential of a foreign technology back to their northern forges. Only a select few master smiths, perhaps a single guild or family, knew the precise and secretive process of working this exotic steel and inlaying the distinctive Ulfberht inscription. The name itself remains enigmatic, possibly that of a revered founder or a workshop trademark. By the 11th century, as trade routes shifted or were severed, the supply of the crucial raw material dried up. The knowledge of how to forge it faded, and the Ulfberht swords passed from practical weapons into the realm of heirloom and folklore. They stand as a stark reminder that technological advancement is not always a continuous upward climb, but can be a fragile flame, dependent on distant trade networks and guarded secrets, a flame that can be extinguished by the changing currents of history. This brings us to our final and perhaps most profound category of ancient mystery, one that moves beyond the physical mastery of materials and into the realm of organizing knowledge itself, to a system of information storage so elegant and durable it has survived for millennia while its meaning remains just out of reach. The Ulfberht sword was a marvel of imported material science, but some ancient technologies required no trade routes, only a patient, upward gaze. Across the globe, from the wind-swept Salisbury Plain to the cloud-ringed peaks of the Andes, our ancestors built monuments that doubled as celestial clocks. These were not just places of worship or gathering, but sophisticated observatories engineered in stone, a testament to a technology of the mind honed over countless generations. At Stonehenge, the summer solstice sunrise aligns perfectly with the heel stone, casting a beam of light into the heart of the stone circle. At Machu Picchu, the carved granite pillar known as the Intihuatana, or hitching post of the sun, casts no shadow at the exact moment of the spring and autumn equinoxes, a phenomenon that still draws visitors who witness this ancient calendar in action. These precise alignments are not lucky accidents. They are the result of systematic, long-term observation. Archaeoastronomers, scientists who study the astronomy of ancient peoples, point out the incredible consistency. The Mayans calculated the solar year to be 365.2420 days, a figure more accurate than the Gregorian calendar used in Europe centuries later. The builders of the Great Pyramid aligned its sides to the cardinal directions with an error of less than 1/15 of a degree. How was this possible without lenses or telescopes? The answer lies in a tradition of meticulous record-keeping that spanned lifetimes, even centuries. Imagine a priest or a sky watcher in a Neolithic society. Their entire cultural rhythm, when to plant, when to harvest, when to hold ceremonies, depended on the heavens. They would have marked the horizon, noting the exact point where the sun rose each day. They would have tracked its slow drift northward in the spring, its pause at the solstice, and its retreat southward in the fall. Over decades, these observations, recorded in oral tradition or in marker stones, would reveal the precise cycle. A notch carved on a rock, a post aligned with a distant mountain peak, these were their data points. This cumulative knowledge, passed from elder to apprentice, became a living library. It allowed cultures as disparate as the ancestral Pueblones of the American Southwest and the ancient Egyptians to predict eclipses, to track the complex 18.6-year cycle of the moon, and to create calendars that harmonized solar and lunar cycles. This represents a different kind of advanced technology, one built not from metal or stone, but from disciplined attention and shared memory. It was a science of patterns, recognizing order in the apparent chaos of the moving sky. We, with our satellites and computer models, can calculate these cycles instantly, but we have largely lost the intimate, embodied knowledge of watching the sky's slow dance year after year. These silent stone sentinels remind us that the greatest instrument in this ancient science was the human mind, trained to see, to remember, and to build a legacy in alignment with the cosmos itself. These scattered masterpieces, from the gears of Antikythera to the silent domes of Persian ice houses, are not merely isolated curiosities. When we step back and view them together, a series of profound patterns emerges, revealing not just how these technologies worked, but why they vanished and what their loss truly means. The first and perhaps most striking pattern is the seamless fusion of empirical science with spiritual purpose. For these ancient innovators, there was no divide between observing the world and honoring its sacred order. The Mayan architects who encoded the call of the Quetzal into their pyramids were both acoustic engineers and priests, building a bridge between the physical and the divine. The Nazca people, plotting vast constellations on the desert floor, were master surveyors engaged in what they saw as a direct dialogue with the gods. Technology was not a separate discipline. It was the physical expression of a cosmology, a way to make the invisible rhythms of the universe tangible and permanent. This deep integration gave these projects their monumental scale and enduring cultural commitment, but it also made them vulnerable. When the belief system that animated them faded or was shattered by conquest, the practical knowledge often faded with it, seen as inseparable from the spiritual context that had given it meaning. A second common thread is the ingenious use of hyper-local materials. These were not technologies of global supply chains, but brilliant adaptations to immediate environments. The Romans did not invent a universal concrete. They discovered the reactive magic of the specific volcanic ash from Pozzuoli. The Persian engineers harnessed the dry desert wind and the cool water of underground qanats in a single, elegant system. The makers of Damascus steel relied on trace elements found only in particular Indian ores. This localized genius created solutions of breathtaking elegance and efficiency, but it created a profound fragility. The knowledge was locked to a place and its specific resources. If the source material was depleted, or if the community that understood its properties was dispersed, the technology could not be easily transplanted or replicated elsewhere. It died where it was born. This leads directly to the third pattern, the role of secretive, centralized knowledge. From the single family said to guard the formula for Greek fire to the master smiths who alone knew the Ulfberht inscription, advanced technical knowledge was often a closely held commodity, a source of power and prestige. It was transmitted through tight apprenticeships and guilds, protected as a sacred trust or a state secret. This secrecy ensured quality and control, but it built a single point of failure into the system. If a guild was dissolved, if a master died without an heir, or if a library holding the sole copies of plans was burned, the chain was broken irrevocably. The knowledge vanished not because it was ineffective, but because it was too effectively guarded, too concentrated in too few hands. Oral traditions, while resilient in stable societies, could evaporate in the face of societal collapse, leaving behind only the physical artifacts, silent and incomprehensible. So what do these patterns tell us about the nature of progress itself? Our modern narrative of technology is often a story of linear, cumulative advancement. We build upon the past layer by layer, but the testimony of these 20 mysteries suggests a different model, one of peaks and valleys. Human ingenuity can reach astonishing heights in one era, in one particular cultural and environmental niche, creating solutions so perfect they seem to defy time. And then, through a confluence of social upheaval, lost resources, or broken chains of transmission, that peak can be abandoned. The valley that follows may last for centuries. The Antikythera Mechanism had no equal for over 1,000 years. The recipe for Roman concrete was forgotten for a millennium. This is not a story of stupidity or regression, but one of fragility. It reveals that technological knowledge is not a self-sustaining force. It is a cultural artifact, as delicate and as precious as any manuscript or sculpture. It requires a stable society to nurture it, a tradition to transmit it, and a reason to sustain it. When those conditions disappear, the light can go out, leaving later generations to stumble upon the cold, brilliant embers and wonder what fire once burned there. This realization shifts the entire historical landscape. It asks us to consider that our current technological age, for all its global reach and digital memory, is not inherently permanent. It is another peak built on its own specific conditions, and it forces a humbling, ultimately hopeful question. If our ancestors, with their limited tools and localized knowledge, could achieve such wonders, what does that say about the latent potential of the human mind? What undiscovered peaks might still lie ahead, or perhaps lie forgotten, waiting to be recognized in the silent stones and uncracked codes they left behind? This tapestry of lost knowledge is not a collection of random curiosities, but a map of human potential. From the microscopic carbon nanotubes within a Damascus blade to the astronomical alignments of a pyramid that spans acres, each discovery underscores a single, powerful truth. Our ancestors were not primitive figures stumbling toward the modern age. They were brilliant innovators who solved problems with a deep, intimate understanding of their world. They listened to the whispers of stone, charted the silent music of the stars, and bent the elements to their will with a grace that often eludes our more forceful methods. These 20 mysteries are far more than historical footnotes. They are signposts pointing to entire libraries of knowledge that have since been shuttered, to schools of thought that flourished and then faded from memory. They challenge the comforting narrative of a straight, upward line of progress. Instead, history reveals itself as a landscape of towering peaks and deep valleys, where brilliant civilizations could scale incredible heights of understanding, only to have the path up that mountain forgotten by those who came after. The silence surrounding these technologies is not an emptiness but a question. It asks us to look at the foundations of our own world with a dose of humility and with a renewed sense of wonder. What we consider modern or advanced may simply be one way of seeing, one path up the mountain. The past holds others, so let this journey be a beginning, not an end. Which of these ancient marvels left you the most awestruck? Was it the celestial computer of Antikythera or the unbreakable glass of Roman legend? Share your thoughts below, and if you are hungry for more explorations into the edges of history, be sure to subscribe. Keep questioning the stories we tell about yesterday, for in those questions we often find new ways to imagine tomorrow.